Hi my dear friends, welcome back to our YouTube channel. This is the second type of the problem in the eigenvalues. So to see the question, the matrix is 2 2 1 1 3 1 1 2 2. Once again, this is not the symmetric. Symmetric means the transpose of the matrix is same. A transpose equal to A. So once again, this comes under non-symmetric matrix. But what are the eigenvalues? Let us see that. How to get the eigenvalues of this one? As we know that the eigenvalues of A from the characteristic equation determine A minus lambda equal to 0. This is the 3 cross 3 matrix. So we get the cubic polynomial is of the form lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Plus minus alternatively. What is the S1? S1 is the trace of the matrix, the sum of the leading diagonal elements. 2 plus 3 plus 2, 7, right? What about S2? S2 is the sum of the minors through the diagonals. If I fix the first diagonal 2 here, 3, 1, 2, 2. If I fix the second diagonal 2, 1, 1, 2. We fix the third diagonal, this column and this row eliminated 2, 2, 1, 3. Let us find out the value. 3 2s are 6, minus 2 1s are 2. 2 2s are 4, minus 1. 2 3s are 6, minus 2. So 4 plus 3 plus 4 is 11. And S3 is nothing but the determinant of A. So fix the first column plus minus plus. So 2, right? 3 1 2 2. Okay? Minus 2. Fix this row, this column 1 1 1 2. And finally 1. Fix this row and column 1 3 1 2. So what is the answer? 2 into 3 2s are 6, minus 2 1s are 2. Minus 2 into 2 1s are 2, minus 1. 1 into 1 2s are 2, 1 minus 3. That is 2 minus 3. So 6 minus 2 4, 2 minus 1 1, 2 minus 3 minus 1. So 2 4s are 8, 2 into minus 2 minus 1. So 8 minus 3 is 5. Let us substitute the S1, S2, S3 value in this polynomial. I am getting that lambda cube minus 7 lambda square plus lambda 11 lambda minus 5 equal to 0. 5 is a prime number. 5 is the prime number. So what are the factors of prime number? 1 and 5. That is. So I use the long division method to get the first eigenvalue of the cubic polynomial, and then later on I use the usual factorization technique or maybe the quadratic formula, anything. If I use the long division method, what is the method says that collect the coefficients of the highest to the constant term. So the coefficient of lambda cube is 1, lambda square is minus 7, lambda is 11 and constant term is minus 5. As I told you that this is a prime number, so probably the roots are the 1 and the number itself. So 5 if I consider, plus 5. So adding vertically here, we start from 0, 1 plus 0, 1, 1 5s are 5. So minus 5, minus 7 plus 5, minus 2. Minus 2 into 5 is minus 10. 10, so 11 minus 10 is plus 1. 1 into 5 is 5. Minus 5 plus 5 is 0. So this will perfectly divides. So this is the one of the eigenvalue. Now what about these things? These are the coefficients of lambda squared, lambda and constant. Because there is a coefficient of lambda cube, lambda squared, lambda constant. After getting the first root, this becomes the reduced equation. So what is the reduced equation? 1 into lambda squared minus 2 into lambda plus the constant term equal to 0. This looks like lambda minus 1 whole squared. So lambda equal to 1 comma 1. So hence the eigenvalues are. So see that the eigenvalues are 5 and 1 only. But 1 repeated twice. 1 repeated twice. So this is 5 is the first eigenvalue. I have considered the non-repeated eigenvalues as the first case. So 5 and the repeated eigenvalues are the rest of the case, that is 2. Lambda 2 is 1, lambda 3 is also 1. So how to get the eigenvectors corresponding to these eigenvalues? Let us see. Before going to that, the matrix is non-symmetric but the eigenvalues are repeated. So this is the second type of the problem. Non-symmetric matrix with repeated eigenvalues. Already I have made a separate video, non-symmetric matrices with distinct eigenvalues. So this is the second type, non-symmetric with the similar or repeated eigenvalues. Please kindly go and watch the non-symmetric matrix with distinct eigenvalues. Please kindly go and watch, right? Now, how to get the eigenvectors for this corresponding eigenvalues? As we know that the eigenvectors of A are given by determine A minus lambda into x equal to 0 matrix. It's a matrix equation. Subtract lambda from the diagonal wise. And x is x1, x2, x3 because of this 3 by 3 matrix, right? And right answer is 0, 0, 0. When you multiply the first row with this column, we get the 2 minus lambda into x1 plus 2x2 plus x3 equal to 0, first equation. And the middle row with this x1, x2, x3, we get the second equation. And the similar way, the third one with this, we get the third equation. So this is my star equation. Now, my aim is to get the eigenvector corresponding to these eigenvalues. 5, 1, 1. Let us go for the first case. What's the first case? By putting lambda is equal to 5 in the star equation. So case number 1, putting lambda is equal to 5 in the star equation, in the system of equations, what we get? 5. So 2 minus 5 minus 3x1 plus 2x2 plus x3 is equal to 0. In the second equation, x1, 3 minus 5 minus 2x2 plus x3 is equal to 0. Third equation, x1 plus 2x2, 2 minus 5 is minus 3x3 equal to 0. Substitute lambda is equal to 5. 2 minus 5 minus 3, 3 minus 5 minus 2, 2 minus 5 is once again minus 3. So all these three equations are distinct. All these equations are distinct equations. So what we can do, I can apply the cross multiplication rule. For the cross multiplication rule, I need only two distinct equations. So we can choose any two. I can choose the 1 and 2. What happened? Start the middle variable coefficients. So 2 minus 2. Then x3, 1, 1. Then x1 minus 3, 1. Again back to the x2, 2 minus 2. So this will give the x1 value, this will give the x2 value, this will give the x3 value. Using cross multiplication rule. So x1 by 2 1s are 2 minus 2 into 1 is minus 2. Minus a minus plus 2. x2 by 1 into 1 1 minus of minus is plus 3. And x3 by minus 3 into minus 2 plus 6 minus 1 into 2 is 2. So which gives x1 by 4, x2 by 4 and x3 by 4. All are in the same scale of 4. So when we multiply by 4, we get x1 by 1, x2 by 1 and x3 by 1. So this is the first eigenvector which is corresponding to lambda is equal to 5, 1, 1, 1. Got it? That's right. Now what about the second eigenvalue? 1 only. This 1 only. I need two eigenvectors corresponding to lambda 2 equal to 1, lambda 3 equal to 1. Okay, let us see when we will get two distinct eigenvectors corresponding to the same eigenvalue. Let us see this. Let us see. That's why I consider this problem. It's very interesting. So the case number 2. Case number 2. So putting lambda is equal to 1 in the star equation. Putting lambda is equal to 1. No other lambda values. This is the last value. But if it is possible to generate two eigenvector, it will be decided by the system of equations, star equation. After putting lambda is equal to 1, let us decide. So 2 minus 1, 1x1 plus 2x2 plus x3 equal to 0. First equation. By putting lambda is equal to 1, we get once again the same equation. See that? The third one, x1 plus 2x2 plus putting lambda equal to 1, 2 minus 1 is x3. So please see that these equations are identical. These equations are same. So we can't use the cross multiplication rule. It completely fails. Once we have two distinct equations, then you can apply the cross multiplication rule. We have the similar equations, don't apply. If you apply, what we'll get? We get 0, 0, 0. For example, say 2 3s are 2 1s are 2, minus 2 1s are 2, 0. 1 1s are 1, minus 1 1s are 0. Then 1 2s are 2, minus 2. So we get 0, 0, 0. But what is capital X? Is the non-zero column matrix. So this is the contradiction to the given definition. So that's why we won't choose the similar equations. So now what we can do? I need the eigenvector corresponding to this eigenvalue. How many? 2. Because 2 eigenvalues are equal. So we get 2 eigenvectors. After substituting lambda equal to 1, I found that these equations are identical. What is the equation represents? Is simply x1 plus 2x2 plus x3 equal to 0. So I need 2 distinct eigenvector corresponding to the same eigenvalue. The idea is very simple. What is the idea? You can assume that x1 0, you will get one equation, one vector. If you assume that x2 0, you will get the second eigenvector. If you assume that x3 equal to 0, it will generate the third eigenvector. I need only 2 eigenvector corresponding to the lambda equal to 1. So I can go any 2 cases. So here, when I choose x1 equal to 0, what happened? This equation becomes 2x2 plus x3 equal to 0. So once when we solve the eigenvalues and eigenvectors for 2 by 2 matrices, please kindly go and watch the separate video for 2 by 2 matrices, eigenvalues and eigenvectors. The same idea here I am going to use 2x2 plus x3 equal to 0. So this means that 2x2 equal to x3. So x2 by x3 by. What is x2 by x3 by? Cross multiplying the coefficients to the next side. So 2 comes here, then minus 1 comes here. The coefficients cross multiply the other side. So this will give the second vector, eigenvector, which is corresponding to the x1 equal to 0. So what about now my assumption? x1 is 0. What about x2? Minus 1. What about x3? 2. This is the one eigenvector when we assume in that x1 0. Okay, when we assume that x2 0, what I get? What we will get? Yeah. When we assume that x2 equals 0, this equation becomes x1 plus this x2 0 now, x3 equal to 0. That means that x1 and the x3 are minus sign. That means that x1 by x3 by. So what's the coefficient of x1? 1. What about the coefficient of x3? Minus 1. So what about the eigenvector? x1, x2, x3. Now x1 is minus 1, x2 is 0, my assumption, x3 is plus 1. Otherwise you may write 1, 0, minus 1. This is also correct because as I told you that retain the minus on the next side, this becomes plus 1. If both are similar, both are same. So I get the two different eigenvectors corresponding to the same eigenvalue lambda equal to 1. So that is my requirement. That's it over. What about when x equal to 3? When suppose when x3 is equal to 0, what happened? When x3 is equal to 0, what happened? When x3 equal to 0, this becomes x1 plus 2x2 is equal to 0. That means that x1 equal to minus 2x2. Otherwise, x1 by minus 2 and x2 by plus 1. So the third eigenvector is x2 minus 2, x2 1 and x3 0. So this is also the right answer. But here my requirement is only the 2 eigenvector because of lambda equal to 1 repeated how many times? 2 times. That's why. So once again I repeat that these equations are identical. It may generate more number of eigenvectors. We can assume that x1 0, we can assume that x2 0, we assume that x3 0. So how many eigenvectors we require? We can pick according to our requirement. But once these equations are distinct, then use the cross multiplication rule, we will get the unique eigenvector. Once I repeat this, these equations are identical, same, eigenvectors are different. Once the equations are different, which will give the unique eigenvector. That is a separate video. Please kindly go and watch. Non-symmetric with similar repeated eigenvalues, and that too these equations are distinct. That is the third category. Okay, thank you so much for watching our YouTube channel. Please kindly subscribe our YouTube channel ADC Max for getting more and more interesting video lectures under these matrices. Thank you so much.